Hello, my name is Oscar, and today we're going to work on examination chapter 7 and chapter 8. We're going to start with the first exercise. For the first exercise, the values that we have right now, we have a mass that is equal to 0.240 kilograms. This is going to be the mass. Now we have the spring constant. So K is going to be equal, that is equal to 6 newtons. 6 newtons per meters. That's the spring constant. Now we have the stretch or the compression distance. That's gonna be equal to 0.100 meters. And now we have our velocity that is equal to 0.400. Velocity is equal to 0.400 meters per second. So now to find the mechanical energy, we're gonna use the formula E equals 1.5 times mass times velocity to the power of 2 plus 1.5 times the constant times the stretch to the power of 2. So like we know the corresponding values, we're gonna plot the numbers. So that's gonna be equal to E equals to 0.5 times 0.240 times 0.400 to the power of 2 plus 0.5. 0.5 is equal to 1 over 2. So 0.5 times 6.0 times 0.100 to the power of 2. All of this is going to be equal to E equal to 0.0192 plus 0.0300. And the result of these two values is going to be equal to 0.0492, or you can change the number. I mean, it's going to be the same result, but we can do 4.92 times 10 to the power of -2 joules. So this is the answer for the mechanical energy, knowing the values of mass, spring constant, stretch or compression distance, and velocity. And this is the formula that we use. So now for part B, we need to find the spring stretch when glider stops. So we already have mechanical energy, which is equal to 4.92 times 10 to the power of -2 joules. We also have K, which is equal to 6.00 newtons over newtons per meters. So we have the mechanical energy and we have the spring constant. Now to find the spring stretch when glider stops, we're gonna use the formula E equals to 1.5 times K times x to the power of 2. We also know x. I mean, we don't know x, we need to find x. So now, what we are going to do is isolate x, so x is going to be equal to the square root of 2e, or 2 times mechanical energy, over the spring constant. So x is going to be equal to the square root of 2 times 4.992 times 10 to the power of negative 2 over 6.00, and the result is going to be x equals to 0.128 meters. So this is going to be the distance of the spring stretch. So we have mechanical energy, we have the spring constant, we have so now for part C, we need to find the work done by friction. So again, we have mass, which is equal to 0.240 kilograms. We have the spring constant, which is equal to 6.00 newtons per meters. We have x1, which is equal to 0.100 meters. This is going to be the initial stretch. X2 is going to be the final stretch. Which is the value that we just found. Oh, no, I'm wrong. My bad, this is going to be 0.112 meters. And we have the speed, which is equal to 0.400 meters per second. So now to find the work done by friction, we have the formula 1.5 times K times open parentheses, and this is going to be x2 to the power of 2 minus x1 to the power of 2, and you close the parentheses, and now minus 1.5 times mass times velocity to the power of 2. So now we have 0.5, which is equal to 1 over 2 times 6.00 times 0.112 to the power of 2 minus 0.100 to the power of 2, close parentheses, minus 0.5, open parentheses, is going to be 0.240 times 0.400 to a power of 2. After do the operations, we're gonna have work done by friction is going to be equal to 0.00763 minus 0.0192, and this is going to be equal to negative 0.0116 joules, and we can change this to negative 1.16 times 10 to a power of negative 2 joules. This is going to be equal to this, but we just move the point 2 units to the right. Yeah. So this result is the work done by friction. So now for part D, we have we need to find the coefficient of kinetic energy. So now that we have work done by friction, which is equal to negative 1.16 times 10 to a power of negative 2 joules, we have the mass which is equal to 0.240 kilograms. We have gravity, and this is going to be 9.8 or 80 meters per second to a power of 2, and this we have the differential of stretch, which is equal to x2 minus x1, which is equal, this is the final stretch and this is the initial stretch. So this is going to be 0.112 minus 0.100, and this is going to be equal to 0.012 meters. So now, to find the coefficient of kinetic energy, we have the formula of work friction, which is equal to minus So now to find the coefficient of kinetic friction, we have the formula coefficient of kinetic friction is equal to negative work done by friction over mass times gravity times the difference of stretch. So this is going to be equal to negative 1.16 times 10 to the power of 2 over 0.240 times 9.8 times 0.012, and this is going to be equal to 0.410. So this is the coefficient of kinetic friction, and this is the last part for the first problem of the first exercise from chapter 7 and 8. If you want to make a diagram of this exercise, it will look something like this. This has a mass. Now we have our spring. This is going to be K. This is going to be X. And we have the velocity going to this side. This is how our diagram will look, something similar to this. So now for the last part of this exercise, we need to express our answers in terms of the variables. Variables. Okay, sorry. So we're gonna start with the speed at separation. So we have mass, we have the spring constant, we have the compression distance, and we have gravity. So gravity or acceleration. So this is going to be the mass of the block. This is going to be a spring constant. This is going to be the compression distance. And this is going to be gravity or acceleration. So the formula for energy conservation is going to be 1.5 times the spring constant times the compression distance to a power of 2, so d to a power of 2, and this is going to be equal to 1.5 times the mass of the block times the final speed to the power of 2 plus mass times gravity times the distance, times the compression distance. So now we have to isolate velocity. So to isolate velocity, we're gonna move velocity right here. So, and this is to the power of 2, so we know it's going to start with a square root. Now, we're gonna have K, spring constant, over mass, because if mass is multiplying, it goes to the other side, so it's going to divide. So we have K over mass times compression distance to the power of 2 minus 2 times gravity times compression distance. So right here we go. This will be the answer. So right here we move. So now for part F, we have the total vertical. We need to find the total vertical distance. So we have mass once again, we have the spring constant, we have the compression distance, and we have gravity or acceleration. And so we're gonna use the next formula, which is going to be 1/2 times K times D to the power of 2 equals to M times G times D. So now we need to isolate D. So D is going to be equal to KD to the power of 2, and these two are gonna go over here, and they're, instead of multiplying, like they're multiplying in this area, they are multiplying. To move them to this side, they're gonna start dividing, and we have 2 here, so it's going to be 2 times m times gravity. So remember, mass, spring constant, compression distance, gravity, or acceleration. The formula is here, 1.5 times spring constant times compression to the power of 2 equal to mass times gravity times vertical distance. If it is multiplying, it goes to the other side and starts dividing. So vertical distance, or total vertical distance, is equal to the spring constant times compression distance times the compression distance to the power of 2 over 2 times mass times gravity. And now for part G, we need for part G, we have a cylinder with friction in vertical tube. So once again, we have mass, we have the frictional force, we have the spring constant, and we have gravity or acceleration. So our formula is going to be mass times gravity times x equals to 1.5 times spring constant times x, which I just forgot the name. If I'm not wrong, it is the stretch. Yeah, the stretch. Plus friction. So now we need to isolate x. So we're going to do, let me see, x is equal to 2 times mass times gravity minus F over X. I mean, over K. So this will be the answer. So this is the distance that the cylinder descends before it comes to momentarily rest. So that's it. That will be all the exercise for part 1, or problem number 1. Thank you.